Welcome to the tutorial on how to use ClamAV CUDA. First, you need these things: a CUDA capable GPU, the latest GPU driver, CUDA 5 toolkit, Microsoft Visual Studio 2010 Professional, ClamAV 0.97.6-CUDA. The Visual Studio should be a professional version because the ClamAV cannot be built in the Express versions. The project ClamAV SLN can be found within the Win32 folder. The main file that was edited is the matcherac.c and converted into matcherac CUDA.cu. The file is located within the libclamav folder. Let us open the file. As said earlier, matcherac CUDA.cu, the main file, was within the libclamav folder. There. But let us open the solution within the Win32 folder, ClamAV SLN. Click on the libclamav project, resource files, and open matcherac.cu. As you can see, the libraries of CUDA are not yet included. There are configurations that must be made in Visual Studio for you to build the solution. First, you have to change the build customization of the project to CUDA 5 and add this line in the additional dependencies. The include and the library directories must also be added. Let's go back to the solution. Right-click on the libclamav project, build customization, choose CUDA 5, OK. Right-click again, go to the properties. Under configuration properties, go to VC++ directories. In the include directories, click the down arrow, edit, add file, click on the button, go to C, program files, NVIDIA GPU Computing Toolkit, CUDA version 5, and select the include folder. OK. And in the library directories, do the same. It's also located in C, program files, GPU Toolkit, CUDA version 5, and in the lib folder, choose the folder of your target platform, Win32 or x64, but in my case, x64. OK, apply. And in the linker input, in the additional dependencies, write the line $, open parenthesis, CUDA toolkit lib dir, close parenthesis, slash CUDA rt.lib, and a semicolon. Apply. OK. You can now see that the Visual Studio now knows the path, the libraries, and headers that are used in the file. Now to install ClamAV CUDA, just build the solution. The setup file will be located in the debug folder of setup x86 or x64. Let's build the project. This may take a while, so let's just get back to it. Now that it's finished, let's go to setup x64, debug, and run the setup. Just click next. Choose a directory where you will install ClamAV. In my case, I will just install it in C, ClamAV. Next, next, and wait for the installer to finish. Let's close the installer. Now, to use ClamAV CUDA, you have to open a command prompt and go to the directory where installed ClamAV CUDA. Use the command clamscan to scan files and directories. You have to specify the directory and must be enclosed in quotation. To scan subdirectories inside there recursively, you can use the -r option. To put scan logs in a file, you can use the option -L and the file that you want to save the scan logs to. You can use -D to choose a specific database file or a directory containing supported database files. Let's try it. Open a command prompt. Go to the directory where you installed ClamAV. In my case, C ClamAV. Let's try ClamScan. On this point, the virus signatures from the main database of ClamAV are being initialized. If you only type ClamScan, ClamAV will only scan immediate files in the directory. Subdirectories are not scanned. There, it took 17 seconds to scan the files within the ClamAV directory. Now let us try scanning one of the datasets that was used in the study. The dataset includes data files that are common in a regular computer. In this scan, let us use the -R option to scan the directory recursively and the -L option to save the logs in test.out. Again, this part is where the virus database is being initialized. As we can see in this scan, all the files are clean. Let's skip to the end. In every scan, a scan summary is prompted by ClamAV. You can see that the scan time is 4 minutes 51 seconds. Let us look at the log file within the ClamAV folder. It is on the test.out file. You can see the scan summary. Let us look at my ClamAV directory. You can see that I have two database folders, the database and database 2. Database 2 contains the virus signatures for my test files. Now let us try scanning the same dataset using the -D option and specifying the database. We will use database 2 because it contains virus signatures for every file. In this implementation, pattern matching is parallelized in the GPU. The files are put in a file buffer and then match its signatures to the signatures from the virus database. If a potential match is found, it will be copied back to the CPU for verification. The non-potential matches are discarded from the file buffer. We can see that the scan time of the files with virus signatures are much faster than files with no signature. Now if we look at test.out again, we can see that the scan logs of the next scan was appended, but this time, the files which are infected were also included in the scan log. Scanning files with virus signatures are much faster because the matcher can easily identify it as a potential match. For more information about ClamAV, you can read clamdoc.pdf located in the docs folder of ClamAV. ClamAV offers other useful tools such as FreshClam, which updates the virus database, and SigTool, which was used to create custom signatures that were used in the test files. And that's it. That's the ClamAV scanner with CUDA support. Thank you.